Hello everybody, my name is Simon Križnik, and this presentation is about optimization with Optistruct. I will begin with a brief overview of HyperWorks suite. Then I will focus on Optistruct optimization, and I will conclude with a live demonstration of lattice optimization. HyperWorks is a simulation solution for rapid design exploration and decision making. As one of the most comprehensive CAE solutions in the industry, HyperWorks provides a tightly integrated suite of best-in-class tools for modeling, analysis, optimization, visualization, reporting, and performance data management. Optistruct has matured into a multi-physics solver in an integrated platform capable of multidisciplinary optimization of complex products in a cost-efficient and timely manner. Possible combinations of physical phenomena include structural, fluid dynamics, thermal, multi-body dynamics, acoustics, controls, hydraulics, and electromagnetic solutions. Firmly committed to an open system philosophy, HyperWorks continues to lead the industry with the broadest interoperability to commercial CAD and CAE solutions. Leveraging a revolutionary pay-for-use token-based business model, HyperWorks delivers increased value and flexibility over other software licensing models. The simulation-driven design has been a key philosophy at Altair since the beginning. Solver functionality is built on a foundation of optimization, providing tools not only to analyze but to actually optimize product performance. The Altair Partner Alliance effectively extends the HyperWorks offerings to over 150 applications at little or no incremental cost. The traditional design is based on prior knowledge, engineering experience, and simple trial and error, which is a costly and time-intensive process that still may fail to identify optimal structures. In the simulation-driven design, the CAE is integrated at the very beginning of the design process and assists in design creation, resulting in lighter, more efficient and cost-effective designs. Although optimization can be used at any stage in the design process, using these methods early in the concept development will ensure the most efficient distribution of materials and loads while saving time by replacing costly design iterations. A simulation-driven design process generates improved, more robust and cost-effective designs within a shorter design cycle. Incorporating simulation and optimization early in the design cycle helps shape the concept design so fewer iterations and rework are necessary as the design matures. The strategic and systematic usage of optimization generates design alternatives, trade-off information, design sensitivities, and balanced design to actively support the product design process throughout the development cycle. Product design is a complex process considering multiple objectives, requirements, and constraints, all of which need to be satisfied. The designer is under pressure to meet time targets, performance targets, and cost targets. For example, vehicle designer need to find a balance between aesthetics, functionality, cost efficiency, durability, and safety while meeting deadlines. A wicked problem. It is not well defined, involves stakeholders with different perspectives, and solutions are better or worse, not true or false. Solving wicked problems based on intuition or trial and error is inefficient in today's competitive environment. Design thinking is useful in tackling problems that are ill-defined by reframing the problem, creating many ideas in brainstorming sessions, and adopting a hands-on approach in prototyping and testing. Design thinking is an iterative, non-linear process in which we seek to understand the problem, challenge assumptions, and redefine problems in an attempt to identify alternative strategies and solutions that might not be instantly apparent with our initial level of understanding. It helps us in the process of questioning the problem, questioning the assumptions, and questioning the implications. There are 5 stages in the process. Understand the user, define users' needs, their problems, and your insights. Ideate by challenging assumptions and creating ideas for innovative solutions. Prototype to start creating solutions. Test the solutions. The designer can complement their own creativity using machine creativity. Optimization can deliver innovative configurations that may never have been conceived without suggestions from the software. Design space exploration and structural optimization systematically and automatically investigate large numbers of design alternatives to identify those with the most optimal performance. Optistruct, Inspire, and Hyperstudy can be used as part of a holistic simulation-driven product development cycle. In the early stages of a new design, many factors need to be considered. Hyperstudy is used to explore design alternatives for the entire system and understand the trade-offs. Once a design alternative that strikes an acceptable balance is identified, targets can be cascaded to subsystems and components for further optimization. Inspire is used to develop structural concepts meeting basic performance requirements, while Optistruct is used to fine-tune the designs. In structural optimization, it is assumed that the problem can be formulated before the search and convergence begins, which is good at providing a specific answer to a specific question. The concept design begins with the definition of boundary conditions and package space. Topology optimization is then performed and the results are interpreted considering manufacturability. In the detailed design phase, buckling and stress constraints are included in the size and shape optimization. Finally, the solid geometry is extracted into CAD. In this example of an innovative RIP design, the weight saving over 500 kg per aircraft was achieved. Design exploration assumes that the optimal design is initially unknown and uncharacterizable. The divergent process of design exploration discovers many design variants by performing the design of experiments. Once the more promising designs are known, the final solution can then be found through a converging design optimization algorithm. This is a multidisciplinary design exploration example of a body in white, considering crash and NVH requirements. In the pre-processing stage, multiple models are imported, design variables linked and responses defined, after which the design of experiments is run. In the post-processing stage, the meta-models are generated and optimization is run on these approximations. The optimization results have to be validated in the end. Optimization is a process of automatically changing the design variables within the design space to find the optimum design while satisfying all the required design constraints. The optimizer starts with the initial configuration and asks the analysis software to evaluate the responses, the mass, stress, and deformation. The optimizer then evaluates the sensitivity of the responses to the various design variables and decides which to change and by how much. When the design variables change, the responses change too. So, the optimizer would again need to ask the analysis package to evaluate the responses. This iterative procedure would continue until the optimizer concludes it has found the best possible design for the given constraints and variables. Structural optimization is based on gradient search method, which uses the slope of the curve to move from the initial configuration to the final solution. So, it is susceptible to finding a local optimum. While design exploration methods improve the chances of finding the global optimum, no algorithm can guarantee that the optimum found is in fact the global optimum. The optimization problem may be over-constrained, so relaxing constraints and design variables allow more design freedom. Unconstrained problems are not appropriate, so some constraints should be included. The optimization is efficient when design variables have an effect on constraint and objective functions. There may be issues with FEA modeling, huge constraint violations in the initial design. The amount of material is not sufficient to satisfy member size constraints. Combining too many responses during concept design. Design variable is a structural parameter that is allowed to change during an optimization. Typical examples include material properties, topology, and geometry of a structure and member sizes. Design variables may be continuous or discrete depending on the type of optimization being performed. Response is a measure of system performance. Calculated or derived values that must be tracked to check whether constraints have been violated or to rank the quality of various design options. Constraint is a restriction placed on a problem by limiting the values that selector response functions of the system can take and that must be satisfied for the design to be acceptable. For instance, the maximum permissible stress or a range of frequencies to avoid. Objective is the goal of the optimization and is a measure of the quality of the design. So here is a theoretical example of a cantilever beam where the force of 2400 newtons is applied at the tip. The objective is to optimize the width and the height of the cross-section to minimize the weight. The width can be between 20 to 40 and the height between 30 to 90. The stress should not exceed 160 MPa and shear stress should not exceed 60 MPa. The height should not be larger than twice the width. This chart shows the mathematical design space. Each one of these lines represents a single value of mass, which is a function of width and height. The process to eliminate combinations that exceed the constraint begins. The green line is the stress constraint, and anything below this line exceeds the limit. The blue line is the shear stress constraint. It can be disregarded as this part of the design space was already eliminated by a regular stress constraint. Another constraint is the height has to be less than or equal to 2 times the width, so anything above this line is eliminated. The overall height has to be between 30 and 90, and overall width has to be between 20 and 40. What is left is this green triangle, and any combination that falls within this green triangle is feasible, which means it satisfies all of the requirements. The objective is to minimize the weight, and the optimum design is found in the direction of least weight contour in the feasible domain. There are 6 optimization types available in the concept and fine-tuning design stage. Topology finds optimized material distribution for a structure within a given package space and identifies efficient load paths. Topography is an advanced form of shape optimization that generates bits or swedges on design space. Free size to optimize the 2D structures where the design variables are thickness of each element. Free shape modifies the structure based on a set of nodes that can move freely on the boundary. Shape modifies the structure based on predefined shape variables to find the optimal shape. Size modifies the structure parameters like shell thickness and beam cross-section to find the optimal design. Topology optimization problems are solved using the density method, known as solid isotropic material with penalization method. The density of each element is varied continuously between 0 void and 1 solid. Intermediate values of density represent fictitious material and are not meaningful. To avoid intermediate densities and obtain more discrete design proposals, a penalization technique is used in which the stiffness of the material is assumed to not be linearly dependent on the density. The topology design process consists of the definition of available package space, boundary conditions, constraints, and formulation of the optimization problem, which is input into the optimizer. The results are interpreted and output to CAD. A concern in topology optimization is that the design concepts developed are very often not manufacturable. Another problem is that the topology optimization solution can be mesh dependent. Manufacturing constraint can also be used for aesthetic purposes, such as enforcing certain design patterns. Minimum member size control specifies the smallest dimension to be retained in topology design. This reduces the checkerboard effect and improves discreteness. Maximum member size control specifies the largest dimension allowed in the design. This prevents the formation of large members and large material concentrations. Pattern grouping provides control over model symmetry. Available symmetry types are 1-plane, 2-plane, 3-plane, and cyclical symmetry. pattern repetition and forces multiple parts to have identical or similar designs. Topology optimization design often contain cavities that are not viable for casting. Imposing draw direction constraints will allow the die to slide in either single or dual draw direction. Available with the single draw option is a stamping or sheet metal manufacturing constraint. No hole option is also available, which prevents hole formation in the draw direction. Extrusion constraints enforce constant cross-section designs regardless of initial mesh, boundary conditions or loads. Manufacturing constraints can be combined in many different ways. In this example, symmetry and draw direction are combined. The free size design variable is the thickness of each element. Topology leads to solid void designs, while free size to continuous thickness changes. It is suitable for the design of composites and machined plates. Topography optimization uses shape optimization with internally generated shape variables. The design region is subdivided into a large number of separate variables, allowing any reinforcement pattern to be created within the design domain. This approach is ideal for maximizing the stiffness of components without adding mass. It can also be used to maximize the frequency of a model. Topography optimization often generates a design that is not obvious. A good example is a tank with an internal pressure load. Compare the results from the topography optimization with the conventional reinforcing pattern on the right. Notice that more ribs do not necessarily equate to more stiffness. OS Smooth is a semi-automated design interpretation tool of structural optimization results for further use in the design process. It is used for geometry extraction, FEA topology or topography reanalysis. Size optimization is used to optimize parameters such as shell thickness, beam cross-section, spring stiffness or Young's modulus. Shape optimization is an automated way to modify the structure based on the predefined shape variables manually created with Hypermorph. The usual shape variables are fillet radii, rib height, channel depth or width, or solid cross-sections. Free shape optimization is a simplified shape optimization where no user-defined shape perturbation vector is necessary. Multi-model optimization links the design variables from multiple models and enables to achieve common optimum designable parts. Reliability-based design optimization reduces the effects of probabilistic characteristics of design parameters on design performance. Fatigue optimization enables uniaxial, multi-axial, factor of safety, seam and spot weld fatigue optimization. Composite optimization is a three-phase integrated process guiding the design from concept to completion. Free sizing optimization is used to generate design concepts. Sizing optimization is performed to control the thickness of each ply bundle. Ply stacking optimization is applied to determine the detailed stacking sequence. Composite-specific manufacturing constraints are available. Nonlinear contact and material are supported for all optimization types. The available responses are contact pressure, Neuber stress, gasket pressure, C-gap force, and plastic strain. Thermal optimization can be performed for pure thermal optimization problems or coupled thermal structural optimization problems. NVH optimization is supported for all optimization types. The available responses are tracking both frequency, radiated power and sound pressure level. Equivalent static load method is an optimization technique for designs undergoing dynamic loads such as multi-body dynamics problem, including flexible bodies and nonlinear responses from implicit static analysis, implicit and explicit dynamic analysis. Multiple materials could be more efficient in structural design to obtain a good balance between stiffness and energy absorption, efficiency and cost. A fail-safe structure is designed to survive normal loading conditions even when partial damage occurs. The structure is divided into damage zones and multiple models are generated, wherein each model is the same as the original model. minus 1 failure zone. Lattice structure optimization creates blended solid and lattice structures suitable for 3D printing. The solution is streamlined through two optimization phases from concept to detailed final design. The first phase is similar to regular topology optimization, except in the end, the intermediate densities are converted into an explicit lattice structure. In the second phase, the lattice member dimensions are size optimized. Overhang angle constraints helps to determine optimal structure while either avoiding all overhanging members or finding a good compromise between the structural performance and the need for a support structure in additive manufacturing. Multidisciplinary design optimization enables multiple disciplines to be combined in a single optimization problem. If more than one optimization type is defined, for example both topography and topology optimization, Optistruct will automatically perform the combined optimization. Global Search option performs an extensive search of the design space for multiple starting points to improve the chances of finding a more global optimum. This live demonstration will show a two-stage lattice optimization process from concept to fine-tuning phase and reviewing the results. The first phase represents isotropic material optimization, since the lattice microstructural representation has isotropic homogenized properties. The size optimization phase is aimed at incorporating some anisotropy to the lattice structure, thereby making the structure more efficient. The design space is a frame component mesh with hexahedral elements. The design variables in the first stage are densities of each solid element, and in the second stage radii of lattice beam elements. The weight of the frame is constrained to be below 0.8 kilograms. The first phase stress should be below 0.5 GPa and the second stage stress below 1 GPa. The objective is to minimize weighted compliance, which is maximizing the stiffness. One plane symmetry pattern grouping is used, which automatically activates minimum member size manufacturing constraint. The units are in kilogram, millimeter, kilonewton, gigapascal, and the linear elastic material is titanium. 4 load cases are adapted from a 2008 research paper by Maestrelli and Falsini. Porosity controls the amount of intermediate densities in the model in the first phase of lattice structure optimization run. This is similar to the penalty applied during a regular topology optimization. There are 4 lattice types available for hexahedral elements and 1 each for tetrahedron, pentahedron and pyramid. Traditional manufacturing methods cannot manufacture medium-dense elements, so in topology optimization, discrete designs are enforced by penalizing medium-dense elements. In lattice structure optimization, medium-dense elements are allowed because 3D printing or additive layer manufacturing can manufacture lattice structures. A lattice is a beam microstructure which is porous, meaning in between solid and void. The lattice beam elements have the property PBML and type rod is automatically assigned for each element. The thickness of this tapered beam element can vary along its length and only circular cross-sections are available. Let's begin by choosing the Optistruct user profile. Next, we'll import the solver deck. Choose demo bicycle frame.fen. Turn on the shaded visualization. Review the beam section collector. We see that the radius is 10 mm. Review the frame component. Load steps: the bump, brake, standing and sitting. The material properties are 150 GPa The Poisson ratio is 0.35. Here are the beam and the solid properties. Now the optimization will be set up. Go to Analysis, Optimization, Topology. Then define the desvar, in this case lattice. Check the P-Solid property selector and select the frame component and click Create. Then on the Parameters subpanel, enter stress constraint as 0.5 GPa and hit Update. We'll also define a one-plane symmetry on the pattern grouping panel. Choose the anchor and the first node accordingly, so the symmetry plane will be in the XZ direction. And click Update. Now we're ready to set up lattice-specific options. The lattice structures are constructed using 1D tapered beam elements. Two types of lattice cell layout are available: tetrahedron and pyramid, derived from tetrahedral and hexahedral meshes respectively. The lattice cell size is directly related to the mesh size in the model. For lattice type, choose one. Lower bound and upper bound fields can be used to specify the range of densities for elements that can be converted into lattice cells. Elements with densities above upper bound remain as solid elements, and those with densities lower than lower bound are removed from the model. The intermediate density solid elements that lie within the density bounds are replaced by lattice structures. Set lower bound to 0.01. The stress value field on lattice continuation line can be used to specify the stress constraint for the second phase. If stress is critical constraint for the design, user should define slightly lower value of stress constraint for phase 1 in the topology panel, so that in the phase 2 the solver will achieve a feasible solution with the actual stress constraint defined in the lattice panel. Then go to Edit Lat Parameter. The beam cleaning procedure occurs at the end of the second optimization phase to remove beams with very low radii. Beam cleaning can be controlled with clean. In this case, no cleaning will be used, as removing beams might increase stress, which is critical to this design. Let LB can be used to verify or automatically set lower bound value. This process aims at generating a model that allows for maximum beam element removal and at the same time retaining reasonable model compliance performance. Porosity defined as low will lead to a final design with mostly fully dense material distribution, and is appropriate if compliance minimization for a given target volume is required. The amount of intermediate densities in a model depends primarily on the penalty applied. This is similar to the penalty applied during a topology optimization. In the optimization view, we can see the newly created cards and review them in the entity browser. Remember the DRCO approach? We'll use it now. Since we already defined the design variables, we need to continue with responses. The first response we're going to create is mesh response. Set the property type by entity and select the property. In this case, we need to select the property type as P-Solid and select the frame component. We'll create the weighted compliance response. Here we need to choose the load steps. We can also define weight for each individual load case. Now we need to define the constraints. Let's set up a mesh constraint with the upper bound of 0.8 kilograms. Finally, we set up the objective, which in this case is minimize weighted compliance. Now that our optimization formulation is complete, we can go ahead and run the optimization. While the optimization is running, we can click on Graph and review how the objective function is evolving through the iterations, as well as maximum constraint violations and maximum displacements for each subcase. Also, we can look into the output file. We can see the active constraints for each iteration as well as compliance. Now that the optimization has finished and it is converged, meaning that a feasible design is found, let's again open the output file. Here we see the lattice optimization parameters. Because we set up one plane symmetry, the minimum dimension member was automatically set up. Let's scroll down to the end and review the lattice lower bound check, which is turned on by letLB parameter. In this case, it was adjusted automatically. 3,000 solid elements with low densities were removed and 34,000 lattice beam elements were created. Let's review the result. We can review the evolution of density throughout optimization iterations. Use the ISO contour plot to isolate only elements above certain threshold. Next, we'll import the solver deck from the first phase. At the end of the first phase, a new file with the lattice suffix is generated. This new file includes the 1D element data, which represent the new lattice structure and the sizing optimization setup. You have to redefine the optimization responses, constraints, and the objective function. Here is a warning that unsupported card was imported. And we can see that in the Optistruct let param card, it was inserted automatically. Also, Optistruct Opti control card was defined initial fractional move limit for size. A single design variable is automatically created for each joint of lattice tapered beam elements, representing the radius of all the beam cross sections at a joint. The design variables are related to the radii of each tapered beam element by design variable property relationship entries developed in the size optimization process. Let's first hide the add-on components to isolate only the frame. In the tool Mass Calc, we can calculate the weight of the frame. Let's run another analysis to compare to the first phase optimization results. Meanwhile, we can already go ahead and modify the optimization formulation for the second phase. We'll change the mass response to total and we need to define the list of properties of the stress response. Because now our mass constraint will include also add-on components, we need to calculate the weight of those components. Let's use this number and add to it the frame weight. We can see that the upper bound stress limit was already propagated from the first phase optimization formulation. We can choose on the stress response the normal, shear or von Mises stress. Now that the analysis which ran in the background is complete, we can compare it to the optimization run. Note that the displacement are slightly off. But don't worry, because we're going to improve those in the second phase. Let's open up the animation result. Go to Result, Scalars, C-bar C-beam stress, and set Modal Animation Type. We can see that the bump load case exceeds our 1 GPa stress limit. Other load cases seems to be fine. Let's see how 1D detailed beam representation looks like up close. We can see that the beams are functionally graded. Where most stresses occurs, we have thicker beams at the junctions. Now we can run the second phase optimization, which will take a while. Now that the second phase has converged, let's review the graph. We can see that all the displacements improved and the maximum constraint violation is minimal. Also, the objective is greatly reduced. Let's compare the result of the second optimization phase to the first optimization phase. The objective has still improved. The optimized solver deck. And perform analysis. Final analysis matches exactly the results from the optimization run in the second stage. Open up the animation results. And set the model animation type. Let's review the C-bar C-beam stresses and observe that the bump is now inside the limit. Also, all the other cases seem to be okay. A simple design of experiments was run to explore the trade-off between stiffness and weight. 4 separate optimization runs were performed, each with its own weight constraint, and the resulting stiffness was extracted. Plotting the stiffness versus weight enables the designer to identify the point of diminishing returns. In this case, increasing the weight beyond 0.8 kilograms does not increase the stiffness at the same rate. This concludes the presentation. Thanks for watching.